Okay, so let's continue with the second part. So in this part, we'll try to understand the defects, so point defects having a topological degree for the easy model, that is the Ginzburg-Landau model, where we have oriented gradient field, vector fields. Okay. So and tomorrow we will see what's happening in the like higher target dimension, where we have non-oriented line fields. So it's the theory of Landau-de Gennes. Okay. So okay. So what is a point defects? I've already mentioned it. So point defects of degree E. Okay, so the prototype is the following map. So we take a U star from R2 with values in R2, and let's think that R2 is like the complex plane, and so for each point here, we associate Z over modulus of Z. So that's the modulus, right? So it's the Euclidean norm power D. Okay. So if you like to see this in polar coordinates, then you can write it like this: R is larger than 0, and then you will see here that you have D times the place. Okay. So right, I mean, okay, Arghir already draw. Let me see if I draw as nice as he draw. So this is the origin, which is the singularity. And then for degree 1, what you do is that you will turn once, right? So you have something like this. Okay. So now imagine that you have to turn twice. Then it's like this, but when you will reach here, you have to be in the other, right? So at some point you will go to this, right? So you think, right? So it's like you do this, but you will have to do twice, yeah? So here you have to be over here. So at some point you will have to turn like this, and then you continue turning, right? And then right, it's like periodic, so you're like this, and then you turn back, you're like this. Okay? So this is a smooth map with values in S1, right? So you have that U star is C infinity away from 0 with values in S1. Okay? And this is so the 0 there is what we call a defect. So the prototype of a defect of degree D. Okay. So as Arghir said, this D is the degree. So okay, let me put the degree like this. So what's a degree here? So you take any closed curve around 0, and then you integrate the Jacobian. Okay, so you have that. Okay, let's say that it's S1, but we do it for any other curve, it's the same. So then you get this, and the Jacobian of this is what? Is U star wedge. I keep the notation of Valeria, French notation, sorry. U star, okay, but I give the definition. So A and B in R2. Then A wedge P is nothing but A1B2 minus A2B1. Okay, so it was a question in the previous lecture. So what is the degree in general? So let me do an offline here. So when you take two manifolds, two Riemannian manifolds of the same dimension, the degree is nothing but you take one of the volume of the target manifold and then you integrate the Jacobian. So that's the determinant of the rental of U star. Okay, so that's why. So the question was, what's happening with RP1? So if you do RP1, of course it's an integer. But if you see RP1 like the volume of RP1 like half of the volume of S1, then here you will have like 1/2 of that thing. So that's why you can have half degrees. Okay, so that's nothing special about this. Okay, next. So right, and this quantity, which is the Jacobian, that is right, is the same thing that you write it over here. So if you want, so if you parameterize S1, that is nothing but the derivative, the angular derivative of the angle of the lifting of U star, if you want. Okay, so yes.
Good question. So the first formula involves U, your U star, right?
Yes.
While the second one is only calculating about the derivatives of U.
Right, but the derivative is here.
Yeah, but there's also the function there. Whereas the second one,
I don't understand your question.
so in the first one, it's U wedge product with the derivative.
Right. Yeah. So if you want, so if you see S1 like the 0 to pi periodic, right? And then U star locally, right? Because that will have a jump, like E phi star. This is nothing but D theta phi star. Okay. So that's but again, right? I mean, such a function will never have a smooth lifting. Yeah. So that's the differential. But okay, it's how you write in your chart, right? On your manifold. So, but that's the definition. Okay, let me put it like this. I mean, this is correct, but you should take the absolutely continuous part of this. Okay, but anyway, this is fine. Okay, so
quickly, there's a defect in the first one. Are we thinking of a sort of an isolated point we removed from the manifold M here as well? Extract the point.
No, so careful, right? I mean, there is no. So I take here a curve. There is no defect on the curve.
No, I meant the domain is R to extract the point, so it's the degree of the defect at the point 0.
Right. So you have this property. You have this property that you for any curve that you take here, so when you compute this quantity, you get the same number. That's called the degree of that defect.
So for the manifold, I'm just wondering, you extract the point.
There is no defect on the manifold.
M there is a circle.
There is no defect on the manifold.
That's one.
These functions are smooth.
2 is one.
So I'm not taking. No, I'm not taking the. So if you want it, so this expression, you always have an expression that if you take an extension, so let's take that, say that you take a circle, you take an extension here, so of course that extension is with velocity now 2, and then you compute this thing in that disk, then you get the same thing, because this will nothing be, but you can interpret this as a boundary integral in your integration by parts when you do it in V. Okay. So what is important, because it's right, you have a function with everything S1 and you say, how can I detect the defect? And that's the Jacobian that detects the defect. So the Jacobian detects the defects, right? And in this case, right, so the Jacobian of U star, okay, so for example, you can compute it away from zero, everything is smooth, but this has the same meaning in terms of distributions in the full space. So you get that this is pi delta 0 and times d. Okay, so you will see that the degree comes over here. Okay, so as Arghir mentioned, so such maps have infinite energy. Okay, so if you compute, for example, in a ball, you will get that this is infinity, right? So, for example, if you compute on some annuli between the radius r and r/2, then you will get that this thing goes logarithmically when r goes to 0. Okay, so so that's why these U stars are so-called S1 value harmonic maps. With infinite energy. So infinity with energy. And so again, so when we speak about S1 valued harmonic maps, that's not Laplacian equals 0. You should imagine that you minimize, for example, your Dirichlet energy on the configuration space where these maps are with values in S1. So therefore, you will not have that the Laplacian is 0, but you will have a Lagrange multiplier that will come up. So it's something like this. So I don't want to speak about singularities to give a meaning to this. So I take the classical way and I avoid 0. Okay, so we want to speak about these maps in the theory of Ginzburg-Landau. So why there we can do the theory? Because as I said, if, for example, we would like to minimize here the Dirichlet energy, you will get infinity. So you cannot do classical theory. So Ginzburg-Landau theory, what it does, it will relax the constraint that you are with in S1 and will penalize the fact that you are not in S1 in the energy. So that's the bulk energy that we saw previously. So let's go to the, I put points because Valeria is very rigorous. So let me do with points. So in the model, okay, so everything that I say here is like the introduction of the very nice book where you find almost everything of Betuel, Résis, et Lin. Okay, so what are the maps here? Okay, so see, I put the star there. So star means that your universe is in S1. So now you relax. So let's say that we are looking just to a disk. Okay. And now I'm with values in R2. Okay. And so the energy is this one. Okay. So right. So previously So sometimes you see this in a different way. So let me give you directly the thing. So if you do a rescaling, when I do this, it's like the offline thing. So when you do the rescaling, so this R, you should consider that R is large. So it's like 1/epsilon, and then you take X to be X over R, and you tilde of X tilde equal U of X. Then the energy in U tilde, so the H1 norm in 2D is scaling invariant, so it's the same. But what's happening is that you will have the 1/epsilon squared coming here. Okay, so, and this is in D1. Okay, so sometimes it's also good to think to this. So here I will take R go to infinity. Here we will take epsilon going to 0. So that's why it's good to think over here, because right when epsilon will go to 0, this is what I call that this is a penalization term, but because when epsilon goes to 0, this is infinity. So in order that this is finite, then modulus of U should be 1, right? So that vacuum manifold that Arghir was speaking here, it's S1. Okay. So if you look to this potential, this is the double well potential, right? Okay. So you see here you have 2 minima and 1 local maximum. So you have three critical points, and these so of course it will be unstable. These are 2 stable ones plus 1. By the way, please, I just want to see mistakes at the board. So when you see a mistake, tell me. 5 mistakes, 1 beer. So Thibaut, he knows. Yeah. So okay. Right. Okay. So what is the vacuum manifold here? This is where U is equal 1. So this is S1. Right. So you expect, for example, here that there will be a link, for example, between, you expect that, for example, minimizer under some boundary condition that I speak now will converge to one of that prototype with S1 value. Okay, so boundary condition. So I think the one we want, right? So we can write this like R EI theta. This is the EI theta, right? So this will be on the boundary of the disk. Okay. Okay, so what will be the prototype of the function here? So you can say, okay, let's look to the minimizer, right? And let's see, is this minimizer, does this minimizer have a similar structure? So let's put that the aim would be to understand this minimization problem under this boundary constraint. Okay. So
E is an integer or natural number here?
it's written there. Thank you. Okay, so when you look to a problem like this minimization, there are 3 things you should know: existence, regularity, and uniqueness. Okay, so let's see. Existence, that's nothing but the direct method of capping, right? So this you have H1 with compactness, the energy is lower semi-continuous with respect to this topology, so the minimizer exists. Okay, so this is okay for every R, and the critical point satisfies the PD, which is given by U. So this is in the ball, and U is equal with power D on the ball. Okay, regularity. So it's not difficult to show that when you start with the data that is modulus 1, you can prove that any solution will have the modulus less than 1. So you are L infinity. And then you bootstrap. Okay? You bootstrap, you get to C infinity. If you want more, you apply a Cauchy-Kovalevsky and you get to analytic. Okay? But let's not go into that. And now the tricky question, which is in some sense the question that we raised with all our collaborators. So, okay, because what we explained here, it's the working four. So it's Luc, Valérie, and Arghir. Okay, so it's always the question, what can you say about uniqueness? And let me tell you what's happening. So there are two regimes. So the first regime is when R is small. So what's happening when R is small? When R is small, you should imagine that, right, we have always like the Poincare inequality. So this quantity will control like an L2 norm of U. Right? If the R is small, the constant, so the first eigenvalue is very large. So if you add, so of course this is non-complex. But if you add this parabola with a large constant, then this will become complex. You have a complex functional, then your minimizer, for example, it will be the unique critical point. Okay? So this is yes. So you have uniqueness because, so by convexity of your energy. So now what's happening when R, so right, no matter what D is. Yeah, so yes for every D. Now R is large. So in the case when the degree is 1, then the answer is yes, and that's the book. It's not easy. It's the proof of Baccar and Rivière. Okay. So in fact, you can prove that not only the minimizer is unique, but also the critical point is unique. D equal 1. What's happening now when D is larger than D? The answer is no. Why? The energy. So you will always. So I will show you that you always have a solution that is the invariant with respect to an actual S1 group action in the problem. So that will have degree D at infinity. So if that solution will be unique, then the energy will be like D squared log R. But what you can do is that you can split the degree D in D vortices of degree 1. And then your price will be D times log epsilon, right? It's much less. So that's why there, for example, for d equal 2, you expect to have, for example, 2 vortices, and then of course you can rotate as you want. Okay. So so the answer is no. Right, and we work hard to understand because right the problem is still open even for d equal 1. We don't know what's happening in the yet. So we have R large, R small, we don't know what's happening in R. So that's a big conjecture in Ginzburg-Landau theory. Okay.
What's saying that for the R small regime, that's epsilon to infinity, so that's a regular perturbation. Then, yeah. It's just your comment about the R small being yes, so that rescaling, that's sending epsilon to infinity. The R small.
Yes. Okay. So you can also prove that when R goes to infinity, the uniqueness is still true. Okay, and that's the proof of mirrorness. What I'm saying is R large fixed.
No, I was talking about the R small regime. So just an observation, the R small.
So, sorry, no.
I'm just saying for the R small.
Okay. I mean, I think my theorems are clear, right? So it's written R small. So this means so when R is small means R is less than some R0, and R large is R larger than R1.
I'm just saying to interpret, if you go back to the energy scaling there, it's just that for R small, that's equivalent to sending epsilon to infinity. Yes. So that's like saying you've got a regular perturbation of this Dirichlet energy, just an observation.
Okay, yes, so.
And then the other opposite limit is a singular limit. That's the.
Yeah, but the problem is that, right? So exactly. Right, so when you take epsilon going to 0 there, then you will get to this infinite energy harmonic map. When you take R going to infinity there, you will get to still a smooth, you will still get to a smooth solution where you will, so I will speak now, you will still have a radial profile. Okay, let me continue. So other questions?
Question about regularity. The infinity log or after the boundary?
Very good question. So it's the problem is that you cannot be C. So you cannot be C2. You cannot be C2 on the boundary because you will have a problem. So it's like C1 alpha if you want to go to the full PR, and it's C infinity. Sorry. No. Sorry. No. I'm speaking. Sorry, I'm speaking about the limit. No. So they are C infinity up to the. Yeah, there is no problem. I mean, it's you just do so. Yeah. So you just do, that's nothing but the bootstrap, the elliptic theory. You can bootstrap, right? So you always get, when you get the WKP, so for K large, you are C infinity up to the boundary. No. So that's C infinity up to the boundary. Okay. Fine. So now, okay, so we have existence, but we want to look to a precise solution, which is similar to the prototype S1 value. So the special solution is the one that is invariant with the following S1 group action. So you apply such a thing. Okay, and so you can prove that the only solution. There exists a unique solution that is invariant under this S1 group action. So right, I mean, you see that the boundary condition will be invariant under this one. Yeah. And also the energy is invariant under every orthogonal transformation. So the solution invariant under star is given by the following. So yeah, let's put it like this. It's radial profile, and then we have exactly U star. Okay, so if you want, it's nothing but f of r I d theta. Okay, so right where r is between 0 and 1. Okay, so you can prove that the only solution that is invariant under this is this one. So and then of course, so this radial profile is in fact unique, the unique solution of an ODE. So where f the unique solution of the ODE. So you have an ODE here. Okay. And f is 0 and 0, and f of r is 1. Okay, so let me draw. Right. So you have a solution that behaves like this. This is 1. And this is f. Okay. So you can prove. MV proved it, and so there are a lot of other works. So also we did some work on some general. That's the 4 boys I mentioned. So what they proved is that so this f is unique, f is positive. So f is positive in 0 r. F is increasing. Okay, and here f behaves like r to the power. Okay, so from now on, let me focus on d larger than 0 and d integer. Okay, so yes, please, Marta, ask me. Hervé, husband and wife. So,
Is the D coming into the equation, Radu?
what people follow, let's just be square. Right. So yeah, that's number 1. Good. Okay. So what is this? In fact, this is nothing but the gradient. The gradient of U star. So if you compute the gradient of U star at C, this is nothing but D over R. Okay. So that's why you have this in front of them. Because right in the Dirichlet you have the square. Thanks, Luke. Okay. So okay. So of course, right? As I said, so when R is small, you know that this solution is the unique one. So this solution exists for every R. Okay, so this you will always have this solution. And in fact, as I said, the conjecture for when d is equal 1 is to prove that this is the unique solution, or at least the unique global minimizer for every R. Okay, d equal 1. Okay, and the rest of my talk is nothing but proving the stability of this solution. So when d is 1, and then instability when d is larger than 2, and r is large, because right, we know that there's something, you have this kind of splitting, so that solution should lose the stability. Okay, so that should be okay. I didn't put so that special solution. 3 and now 4 stability. So what I mean by stability, well, you have a functional, and then you will just look at the second variation at your critical point, and you will look to see if it's positive, then it means it's stable, and if you can shoot in one direction and the second variation is negative, then you are unstable. Okay, so right. Okay. So in fact, in the following, let me, in order that you understand better how this potential plays a role, let me consider this more general potential, right? And W you should think like P squared over 2. But as you will see that, so in all the computation, only the fact that W is convex, it's enough. Okay, so for example, here, this is nothing but W prime. So, sorry. Okay. So what is the stability? So stability, so we look to the second variation. And this solution okay, so that's what? That's nothing but the second derivative in one direction where this b does not change your boundary. Okay, so when you do the computation, this is so when you differentiate twice the gradient, that's gradient b squared, and then you have things coming from that part. So that's like 1 over 2 W1 minus U squared. So then you get something of the form V squared W prime 1 minus U squared. So if you want F squared. And then you should have some contribution from W second, and that's like 2U times D squared W second 1 minus F squared, and everything is dx. Okay, that's a computation you can do. And you differentiate. And you get to this. Okay. Yes.
You put the blackboard more up so that the people in the back can see you.
Yes. Yeah. Is it fine?
A little bit more.
You know, when I was a student, it was a talk of Jean Maouin. Jean Maouin is a Belgian guy who's even smaller than me. And he came in a room where the blackboard was really high. But it was not, that thing that used. Okay. And then how he starts the talk, he does this. Imagine that it's like that's like this, and he says, "Every man has a limit." That's my limit. Okay, so I do what I can. Okay, let's see the computations. Yeah, if you see a mistake, you get close to the VM. Okay. So the theorem. So actually, I want to put the theorem there because there we will do the computations. So the theorem that I want to prove now, which is like the core or all the stability theorems we have, or the tools we use, is the following. That is due to Mironescu and partially at the same time of Liebenloos, because they put only the stability for one, Mironescu also put the instability of the other. Okay, so what is the theorem? The theorem says the following. So if D is 1, then our solution is strictly stable. So meaning that the second variation is strictly larger than 0 for every V non-zero. And 2 is that if the degree is larger than 2, then this solution is unstable, meaning that there exists a V such that if you shoot in that direction, you are negative. Okay. So 15 minutes to give you the proof.
Hello? Please, the theory.
Yes.
What's the name? What? I can't see it clearly.
I'm sorry?
The theorem mean what?
Mironescu. The name, yeah. Okay. Mironescu and Liebenloos. Okay. So let's see how much can I do. Okay, so what we do is so the second variation is a quadratic function. So what we do is that we will do a Fourier decomposition, and then we will analyze the modes. Okay. Okay. So Fourier decomposition. So let me write D as A and R, E, I, and theta, right? So these are complex numbers, right? So complex maps, and in R they are 0. If you want, it's enough to take AN to be C infinity compact support between 0 and R. Because then you can, so for example, the full stability, then you can pass the limit to the full H1 because you are in 2D and one point is 0 capacity. Okay, so we have 3 terms. Okay, so let's start with the first one, the Dirichlet term in the second variation. So what's this? So let's do composition. So the gradient is RV Artian. Martha, you have a question? Oh,
AN 0 is 0.
what?
ANR is in C and then is 0. AN is 0.
AN of R. So we are so this V is in VR, yeah?
Capital R.
Capital R.
Just like this last. There are no mistakes.
So Lucia, you're ruling a beer after 5.
I want the beer. I know.
Which is okay.
Okay. No, but this is good. This is good. Thibaut, the students followed my course, isn't it? Yes. Yeah. Okay. They know they get the beer after. Okay. So right. Okay. Then you compute your calculus thing. You use that this is orthogonal, and then you get so from here you get the derivatives, and then when you differentiate here, you have the n squared coming here. Okay, so that's easy. Now the second term, which is this one. So right, so keep in mind that f depends only in R, yeah? So dr minus w prime 1 minus f squared v squared. Okay, so you do the same trick, and then you get minus 2 pi 0 r w prime 1 minus f squared r, and then 8 n of r squared r, yeah. Okay, and now the more delicate term, which is anyway positive, right? So this term anyway is positive. So for a lot of modes, I won't use it, but for the tricky ones, I have to use it. So, okay. So how do you compute first u times v? So what is this guy? Well, that's nothing but the real part of v u bar. Okay, so then this is nothing but f of the real part v e minus d theta. Okay, and now I write that the real part is the z plus z bar over 2, right? So then I get, and let me take the square. And then I get that this is v minus ei theta plus ei d theta squared. And then, boom. Okay. So who's this guy? So that's sum over n of A and R, EI n minus B theta. And who's this guy? This guy is A n bar. So let me put an M. And then I have EID minus M theta. Right? And I want to put them together. So then I call this K. I call this also K. And when we put together, we get that this guy okay, then maybe I want to integrate at some point. Is what? So here you will have only sums of okay. So let me put 0R. And okay, I go directly. So I have f over 4. Then I will have plus 2 pi. And then here I have the W second 1 minus f squared and the sum over k. So right, so this m will be d minus k, and this so n will be d plus k. Okay, so you look to the things where the sum is 2d. Okay, and that's what that's a d plus k plus a d minus k squared r to r. Okay, so I take this, and here you will have a pi. Okay, so see, this is you have what you its matters is 2 pi, 2 pi, and there is only 1 pi. Okay, so now we have this guy which is positive. So as I said, sometimes we will use it, sometimes not. Okay, so now what we want to prove, so up to now the D was anything. So now I want to get to stability. So the first aim is stability for D equal 1 any R. Okay, so from now on D is 1. So I do it in 2 steps. So step 1, I treat modes n that are different from 0 and 2. So for the ones where I have n different than 0, I don't care about that. So it will be enough to, so it's enough to show that this quantity is positive. Okay, so let me call it En. Okay, so I have the 2 pi here. And so that's what? That's a n prime r squared plus n squared and minus. Okay, let me put it together. Okay, let's do it later. Minus W prime RPR. Okay, so what you do now, you just say, well, this guy is larger than 1. So of course, what I do here, you could apply also for 2, but you will see that 2 is needed to treat the 0 more. So then you get that this is larger than 2 pi integral from 0 to r of an operator that I write times the other operator, rdr, where this operator is what? So from here I have the Laplacian, and then I have here a potential, the potential P, which is this guy. So I put 1 over r squared minus w prime 1 minus f squared. So in order to prove that this is positive, you just need to prove that the first eigenvalue of this operator is positive, right? And now you do what we call Hardy decomposition. I mean, a lot in our papers is Hardy decomposition. What do we mean by that? Well, this is, in fact, Picone did it in some other context in 1911. This is a recycled thing. So what you do? So as I said, you can do this for an that is infinity compact support between 0 and r. So what you do there is that you will decompose with respect to a function that plays a role to this f. It's like the first eigen function of that L, and you will see that this is exactly the f times something, right? So this you can do it provided that this f will never vanish in 0r, right? Because this an so avoids the 0 where f is 0, but then you don't, it doesn't matter. Okay, so if you do this, then everything is smooth. Okay, and then you have this identity. So you know it's a spring school. It's good that you have also some homeworks home or your hotel, and just prove by just integration by parts the following identity. You have the following. So if you want, you can go within the ball. So you have LAN is given by f squared gradient of an squared dx plus a hat squared. You could do by components, right? Because this is a C number, but okay. And then you have LF dx. So now let's recall what was the equation of f, which is equal. Okay. So in fact, LF is 0. That's exactly the equation. So you are done. Our is done. Or would I have more questions? Because one more time, because I have 2 questions. The chairman. That's due to Stephen. Or you just blame Stephen for that? Yeah. Okay. I want to omit this. I know that I can do the full book. So let's look to the equation. So let me recall the equation in F. So it was minus Laplacian F plus d squared over r, but this one, right? So it's F over r squared equal F w prime 1 minus f squared. But you see that this is equivalent by saying LF is 0. So if you want, F plays the role, I mean, in some sense, right? Because f is 1 at the boundary, so it's not 0 at the boundary. But you should imagine that it plays the role of like the first eigenfunction of this. So that guy is 0 and that's positive. So you are done. Okay. But then okay, I didn't okay, so those was for the modes. So then you have to treat, so this, as I said, this goes also for mode 2. But as I said, when you want to treat the mode 0, the problem is that you don't have this, you don't control this term. And that's crucial. Otherwise, without this, this is negative. So that's why you have to play with the 0 mode and the 2 mode. Why? Oops, I erased the. Oh no, it's there. So you see that when you treat this, then it's that term. So when k equal 1, then in the last term that we neglected, you have these terms. You have a0 plus a2 squared, and then with the other one, you also have a0 bar plus a2. Okay, so this is important to treat them together. But so it's I have something quick. Okay, I'm sorry, I cannot do this. Okay, and just okay, sorry. My last second is how you do the instability. So that with the instability, right? So okay, then you play with this and you show that E0 plus E2 is also positive. Okay, and then the second part was the instability for the degree larger than 2, and here you have to shoot with the function that has exactly this kind of structure, which is given by something like this: alpha plus beta EID minus 2 theta plus alpha minus beta EID plus 2 with some special alpha and beta, but this you can find it in the paper. Petru, sorry for being late. Yes.
The result about stability and instability, was it asymptotic in R or it's for any R?
Good. So yeah. This so in what I showed, at least for the mode so here was any R, right? And this is also true for any R. You don't use at all just this behavior in 0 R, any R. However, yeah. So again, I wrote it in the theorem. This will work just when R is large, because this alpha and beta, they are related with the, so alpha and beta, they are related with the F infinity, which is like the limit of, let me put F of R, right, which is the profile, of our function. Yes.
Back there. Do you have any intuition why for E bigger than 2 it's stable and not what equals 1, like kind of physical intuition or geometrical?
Okay, so I explain again. So what's happening is that when you take degree 2, let's speak about degree 2. And so you look to the energy of our function that is here. So always we are thinking about this. Okay. Why is that degree 2? So when you compute that the energy that was in the ball of UR, so this solution, so imagine that would be the unique solution. Okay? So the solution of this will be like E squared, so let me put 2 squared. Okay, there is also like a quantized quantity which is 5, which was 1 also, so 5. Okay, but n log r. Okay. So this solution always exists. Okay, that will have this kind of thing. But what's happening? So that would be right. So this solution in the disk is something that here you turn twice. But I tell you that I can do better than that. I can split. So this is 0, right? So that is where I can split in 2 singularities of degree 1. Imagine that you can do this. Then when you compute what's the energy over here, these 2 will have the energies also. Let me call this like the energy of this will be so twice the energy of degree. So if you believe me that this is d, so each for degree 1 is 1. Yeah, so will be okay, there is something wrong because then I get the same. That's 4. Oh, sorry. Yeah, no, the degree is 1. Okay, right. So it's 1 plus 1.
You don't have twice.
You don't have twice, just 1 plus 1.
Twice, there's 1 plus
1. Yeah. Okay. Yeah. So I have to get 2, right? So this is 4, and this is 2. Right, and then again, the quantized 1 and log r. Okay, so this is much larger than that. Okay, so it means that your minimizer should have this thing. So the minimizer always exists, so you have another solution. Okay, so then if you say, is the minimizer unique? The answer is no, because right, you always have this F1 action group that preserves everything. Now the question is, are the minimizer unique within this? That's open. Okay. Okay, sure.
How robust is this result to deforming from, say, a disk to an ellipse? What is the...
Right, okay, but for an ellipse, what's your S1 group?
That's what I'm saying, you're breaking that symmetry, so...
Okay, what do I put?
Oh yeah, I don't know, I was just wondering.
I don't know. Oh, I don't know. It's right, I mean, in general, what you do, right, I mean, anyway, I believe, right, I mean, you will have like the hedgehog, and then you will try to do like, what's the conformal from the disk to an ellipse, and look to that special solution. But right, I mean, what's the rotation, right? Because it's I don't know.
Any further quick questions? Okay, let's take it again.